This session is advances in urine-derived fertilizer development. I'm always very eager to hear this one, learn about people's innovative work in all sorts of different ways of processing and managing urine to add value to it. So this session we do have 15-minute chunks, 10 minutes of presentation, and about 5 minutes of Q&A. We do have to stick to that time limit, so I'll let folks know when you're at the 10-minute mark. You don't have to stop right there, but just know that you have 5 minutes left for talking or Q&A. So our first presentation comes from Jordan Landis. The presentation is Biopolymers as an alternative to petroleum-based polymers for urine-derived control-release fertilizer coatings to reduce microplastic shedding. Jordan Landis is a second-year PhD student at the University, sorry, it says university here. I believe this is the University of Michigan, studying environmental engineering, specializing in biopolymer formulation, environmental microplastic detection, and microplastic remediation in wastewater. And please correct me if I've messed any of that up, Jordan. Go ahead.
Awesome. Okay, let me see if I can share my screen for you all. All right. And can you guys see my presentation?
Yes, in presenter mode.
Okay. Yeah. All right. All right, so thank you for the introduction. I'm really excited to be here. This is my first time presenting at the Rich Earth Summit, so I'm really excited to be sharing my work. So I do have a microplastic background, and a lot of that has come into my PhD work where Nancy's been working with urine-derived fertilizers. So this is sort of the enmeshment of both of our work, but I've been sort of pulled into the urine-derived world, and it's been very, very interesting. But the talk today I'm going to give is the controlled release fertilizer formulations that we've been working with that is utilizing biopolymers and urine-derived fertilizer. So we know that fertilizer helps improve agricultural productivity, and this is imperative for supporting global crop demand as our global population continues to increase. However, conventional inorganic fertilizers are very water soluble and they lead to excess nutrient runoff. And when I mean conventional inorganic fertilizers, I'm referring to diammonium phosphate or triple superphosphate. And I want to give a demonstration here of how we apply our conventional fertilizers, which I'm sure a lot of you are aware of. So if we're applying our conventional inorganic fertilizers as so, and we receive rainfall, because our conventional inorganic fertilizers are so water soluble, they release our nutrients relatively quickly. And you'll see that our plant will be able to uptake these nutrients as they so need it, but this rate of uptake isn't matching the solubilization release of our nutrients. So a lot of these nutrients that are present here in our soil are subject to being transported to local water bodies and creating a host of issues, where in the Great Lakes region, eutrophication is a very great issue that affects a lot of our residents here. And really, there's a whole other issue that conventional inorganic fertilizers are also not sustainably produced, as I'm sure a lot of people have discussed already in this summit. But I wanted to talk about controlled release fertilizers. And these controlled release fertilizers, which I'll be referring to as CRFs, help reduce excess nutrient leaching. And so this is what CRFs look like. They look pretty similar to what your conventional fertilizers would look like. And typically what CRFs are is they utilize a fertilizer core, whether this be our conventional fertilizers or inorganic fertilizers. And what we'll be talking about is utilizing a struvite fertilizer core. But what makes these CRFs different is that they have a polymer coating. And what this polymer coating does is it helps control the release of this fertilizer core so that we can have a better timing of how we release these nutrients into our soil. However, CRFs utilize not biopolymer, but fossil fuel derived polymer coatings for the release mechanism. And so this is a CRF that's on the market right now. And I just wanted to give sort of an idea of what the safety data sheet looks like. And you'll see that the polymer coating is up to 6.5% of your CRF. And these polymer coatings are fossil fuel derived, and they're typically polyurethane, which is a type of fossil fuel derived polymer. And this is a problem because CRFs could be depositing microplastics upwards of 400 milligrams per kilogram of soil. So I wanted to give a demonstration of if this is our CRF application. And while we are having that controlled release of our nitrogen, phosphorus, and potassium, or whatever nutrients that we have in this fertilizer, you're also creating the release of microplastics. And microplastics have been found to negatively impact soil health and productivity of the plant. And through soil health, there's been a lot of studies into the physiochemical side of how microplastics are impacting the dynamics of soil porosity and how water is able to travel through the soil. But also, this creates more routes for environmental contamination and public health exposure. So, we talked about how nutrients that are still present in the soil are able to run off into local water bodies. It has the same issue with microplastics, and it creates aquatic problematic problems just with our aquatic wildlife and also with drinking water treatment plants down the line that have to deal with these microplastics before they're treated into our drinking water systems. So these are all things that we have to consider. But struvite, which is a urine-derived product, is a natural slow-release fertilizer. And I did want to clarify, we just talked about controlled release fertilizers, and these are two established definitions in our community with these controlled slow release fertilizers. So we just talked about controlled release fertilizers where we're able to have a polymer coating and we're able to control the release of our nutrients over time. Whereas slow release fertilizers typically have an initiating factor to delay the release of our nutrients. And when this condition is met, our fertilizers are, or our nutrients are released. And I did just want to make a note that the controlled release fertilizer and the slow release fertilizer definitions are very gray in literature right now, and it's still being tinkered with, and there's still a lot of debate around these definitions. So this is our interpretation of these definitions. And so struvite solubility increases with decrease in pH. So if we have our struvite, which is representing our slow release fertilizer in this instance, its condition for initiating its release of nutrients is low pH. So as pH decreases, we're able to see this initialization and solubilization that releases these nutrients. However, this condition, the struvite performance as a fertilizer, is limited by its low solubility. And there have been some studies that have looked into struvite as a fertilizer in comparison with some conventional inorganic fertilizers. And there were some concerns associated with if struvite was able to provide the initial amount of fertilizer compared to your conventional fertilizer. So, is that nutrient dispersion enough initially for your plant? But this sort of creates the question in our group and in our research that we've been doing is, can we initiate the design of a CRF utilizing struvite? And so this is sort of kind of creating, we want to be able to control the controlled release element of the struvite, although it is already a slow release fertilizer. So this creates a little bit of congestion in how we wanted to go about this design. But we wanted to initiate the design with struvite, but this may also be a design that we implement with other urine-derived forms as we go down the line. So I wanted to give an introduction into what biopolymers are. They're a sustainable alternative to conventional polymers. And I'm going to say conventional polymers, and what I mean by this is fossil fuel-derived polymers. So when you think about plastics, they're typically fossil fuel-derived. So polyethylene, polyethylene terephthalate, these are all conventional polymers. And so biopolymers are polymers that are, one, biologically derived either by plants or microbes, and two, they're biodegradable either aerobically or anaerobically. And I wanted to give some definitions of this just so it's a little bit more tangible. So polylactic acid is a good definition of a biopolymer. These are pretty common in 3D printing nowadays. If you're familiar with 3D printing, polylactic acid is a very common biopolymer used in that. Starch, if you think about starch utensils, they're sort of brown and they're a little bit transparent, but they are on the market right now. And polyhydroxyalkanates, or PHAs, I'll refer to them as, is the biopolymer that we are wanting to work with our controlled release fertilizers. And I did just want to say that polyhydroxyalkanates are actually biopolymers that are created by microbes as carbon stores. So they produce it when they want to have carbon stores to utilize later on. And we're able to extract these carbon stores as a polymer. So it fits the definition that it's one biologically derived. And there have been some studies where PHAs have been applied to soil and they have been aerobically degraded. So sort of how we're mixing this idea of biopolymers and our struvite fertilizer is that biopolymers can be curated to aid struvite in controlled dissolution. So essentially, we want to be able to utilize biopolymers in a way that's favorable for struvite dissolution. And how this will look like is if we have another demonstration here, and these are our biopolymers that have been curated into our controlled release fertilizers, is that we're able to release nutrients at the rate that plants need them for uptake. And the idea is that we keep creating these nutrients. We release these nutrients at a rate that plants uptake them to minimize the amount of excess nutrients that we have for runoff, and also to just increase the capability of our fertilizer to meet its application. So it's a little bit more efficient, I could say. And so this helps us reduce the microplastic to soil pathway. It utilizes a diverted waste nutrient source, which is urine-derived fertilizer. And then it improves the potential of solid UDF as a fertilizer because, we have these liquid forms of product that we want to use as a fertilizer, but agriculturists and horticulturists are used to having solid UDF application. So this is helping us improve the potential that we may be lacking with struvite. Although it has had very promising results, we want to be able to maximize its efficiency. So this is some work that we've done in our lab scheme. So we just did a very simple experiment with sodium alginate, which is essentially where we mixed up some powdered struvite into sodium alginate and we dropped it into calcium ion solution, which allowed it to create these sort of hydrogel-like materials. And while this experiment was very simple and we didn't do a lot of dissolution work with this, it was more of a proof of concept. We don't think that it'll be very scalable, and we don't believe that it's going to be our approach going forward, but it was a good demonstration that biopolymers can be used to sort of encapsulate struvite. So our current and future work, right now we're working on our nitrogen and phosphorus protocol development. Struvite is soluble at low pH, as we talked about. And our nitrogen, well, our phosphorus protocol specifically is a colorimetric method, which is dependent on pH. So it's dependent, or not dependent, but it's important that we look into how our phosphorus protocol varies with pH if we're decreasing our pH to solubilize our struvite. We also want to do some dissolution experiments with our biopolymer coated struvite. And we just want to get a better idea of how it acts in water and how that nutrients are able to come out of our biopolymer coating and how we can better control for it in future experiments, such as a pot experiment. And these are going to be really important. I'm personally very excited for these. And we're going to be taking our biopolymer struvite coated fertilizer and we're going to be putting it in soil just to see how, since it is a biopolymer, it can interact with microbes and how that microbial interaction contributes as well to the dissolution of our struvite and the fertilizer. And that is our work. And I just wanted to give some acknowledgments to the Love Group and especially Nancy, who has been a great advisor and who has been amazing in introducing me to the urine-derived world. It's very great, and I'm very excited to be here. And thank you so much.
Wonderful. Thank you very much for that presentation, Jordan. And shocking how much microplastics can be in those coatings. I didn't realize it could be that large of a fraction. So hope to hear more about that as you make progress. We don't have time for questions on this, correct? Okay. So we'll move right on. If you have questions, just pop those into the chat. And Jordan, if you can keep an eye on that, you answer those as you can through that function. Thank you.
Yeah, of course.
Our next presentation is from Dr. Maria Koulouri. The presentation is an integrated process to enrich fecal-derived biochar with nitrogen and phosphorus from source-separated urine. Dr. Maria Koulouri is a research associate at the Department of Civil and Environmental Engineering of Imperial College London. Her research focuses on resource recovery from wastewater and fecal sludge management systems, circular economy solutions, and innovative sludge treatment technologies. She's an expert in pyrolysis treatment with a focus on the recovery of biochar soil amendments from source-separated human excreta sources. Currently, she is researching systematic circularity assessments and life cycle analysis tools for organic waste streams with a focus on carbon negative innovations.
Thank you so much. Can you hear me? Can you see my screen? Yes, we can both. Thank you.
Perfect. Sorry that bio was very large. I didn't realize when I sent it probably. So thank you, very happy to be here. So this presentation will be about how we can enrich biochars derived from human feces with the nitrogen and phosphorus from the urine. So trying to make the best of both outputs of source separating toilets, essentially. So just to very quickly set the scene, because we've covered a lot of this, when we think about global sanitation systems, on the one hand, we have sewer sanitation and centralized treatment, where human waste are mixed also with large quantities of flash water, black water, gray water inputs. And then on the other hand, we have on-site sanitation that can operate without any water, managed in a decentralized manner, and much more often these toilets are also separating feces and urine. What I think is interesting is that as of 2021, more people globally are using on-site than sewered toilets. And it's safe to say that if we have any chance of meeting the target of universal access to safe sanitation, we are going to have to build more of these toilets, and we are going to have to find better ways to treat and recover resources from human waste. So if we look at the outputs of a dry source separating toilet, on the one hand, we have urine that contain most of the nutrients. They are relatively sterile and so considered safe for use in agriculture after long-term storage. And from a practical aspect, though, the direct application of urine poses a few technical and environmental challenges. So usually what we do is we try to recover the nutrients in urine via some form of treatment and then apply them to agriculture. And there are many methods for this, many different treatment technologies for urine. Two that are quite well understood, low in terms of cost and complexity, are the precipitation of nutrient compounds, struvite was just mentioned, and also the absorption of nutrients on porous media like biochars, activated carbons, or zeolites. Now, on the other side of what comes out of a toilet, we have feces that have very different composition. They are rich in carbon, they're suitable for energy recovery as well. But when it comes to agricultural uses, the main challenge is the pathogen content, of course, which needs to be eliminated via thermal treatment. Pyrolysis is a very promising technology for the treatment of carbonaceous materials like feces. We saw it also on the keynote presentation yesterday, and it's gaining a lot of momentum mostly because of the biochar product, which has many reuse applications, including as a soil amendment, a carbon sequestration medium that is gaining a lot of attention, and also it can be used as an adsorbent. So we see a connection coming up here where if one option for the urine is to absorb the nutrients, and if we can make an adsorbent out of feces, we can then maybe create a circular treatment loop for human waste and make the most of both the soil improving properties of the fecal biochar, but also enhanced with some of the nutrient value of the urine. So for this research, we set this question of how can we optimize nutrient recovery from stored urine via precipitation and adsorption onto fecal-derived biochars. And to answer this, we firstly collected source-separated urine, undiluted urine samples from volunteers. We stored them for 6 months to observe what happens during the recommended storage time by the WHO, and we monitored their nutrient composition and precipitation reactions taking place. We also collected human feces from our volunteers, which was our feedstock for pyrolysis in the lab, and we produced biochars, which we then used as the medium for our nitrogen and phosphorus recovery experiments via adsorption and precipitation. During the urine storage period, in terms of what happens to the nitrogen, over the first month, we saw the typical urea hydrolysis image, so turning into ammoniacal nitrogen. It was a very slow response compared to other systems we've seen because storage was in decentralized containers, not through large tanks or pipes that tend to have active enzymes accelerating hydrolysis. Then the system was pretty much stable for the next 2 months, but during the 4th month of storage, there was another statistically significant jump in ammoniacal nitrogen content for all our replicates, which was accompanied by a simultaneous drop of pH, suggesting there was a dynamic equilibrium between the ammonium and ammonia liquid gas phases in the system of a closed container. After that, the system did stabilize until the end of the 6-month period. So throughout this period, the pH was an indicator of urine stability, I would say, but it should not be confused as an indication of absolute concentrations because these vary greatly between different urine solutions, different urine tanks, etc. In terms of precipitation during storage, we first investigated qualitatively via FTIR, and we mostly saw the peaks associated with phosphates, ammonium, and carbonates. To then confirm and quantify, we monitored the mass balance of nutrients after 1 and 6 months of storage by essentially calculating their elimination rate from the liquid phase. We clearly saw that precipitates were being formed. Elimination percentages for calcium, potassium, and phosphorus were around 30%, and for magnesium, it was more than 90%. So that tells us that magnesium would be the limiting factor for further recovery of magnesium phosphates like struvite. And so if we had more magnesium in the system, we could precipitate more compounds. So by the end of our storage period, we knew that we have a very high concentration of ammoniacal nitrogen, around above 6 grams per liter. We know that the system is stable and fully hydrolyzed, and we know that precipitation of nutrient compounds has occurred. So the next step was how can we now recover this value in a more manageable form than having liters and liters of urine by using our fecal-derived biochar as an adsorption medium. First, we looked at adsorption of ammonium onto the biochar surface. We found a very good fit to both Langmuir and Friedrich isotherms. The adsorption capacity was around 20 milligrams per gram of biochar, and the reactions were complete after 1 day. What is interesting, I think, is that the main mechanism of recovery was not surface adsorption, it was ion exchange, and especially between the potassium ions from the fecal biochar with the ammonium ions in the urine. In terms of how much nutrients we actually recovered from urine, we could extract a maximum of just below 30% of the total nitrogen present in urine. So there is definitely room for optimization. One example could be pH control to increase the fraction of ammonium compared to ammonia. But if we think that the total ammonium content is the total nitrogen content is around 7 grams per liter, 30% of total nitrogen is still 2,000 milligrams per liter. So it's a significant amount that can make the biochar NPK much more balanced. And then in terms of phosphorus, when just adding biochar to urine and nothing else, we saw that the maximum recovered percentage was below 20%. But when we tried adding an external magnesium source, magnesium oxide, based on the storage observations and the mass balance of precipitates, we could then practically recover all of the phosphorus via precipitation. And what I think is interesting here is not that we can precipitate phosphates from urine, we expected that, but in combination with the biochar was an excellent carrier for the formed crystals, and it allowed solid-liquid separation of precipitates by gravity, which was otherwise not feasible. The urine precipitates formed a sort of sludge in the tanks that was very hard to separate even by centrifuge. So at the end, we were able to collect a single product very easily that was a combined biochar soil amendment with the fertilizing value of the urine precipitates. Just to show you a last thing, we also did SEM and EDS imaging to identify what were actually the precipitates being formed rather than just assume based on the mass balance. We saw that the crystals were very well attached on the surface of the biochar, as well as some bigger separate particles being formed. We did identify a lot of struvite, as expected, based on the mass balances. Also, a lot of instances of the potassium-containing analog of struvite, so a crystal that contains nitrogen, phosphorus, and potassium. And also very few quantities, but some apatite crystals as well. Again, with analogs containing not just phosphorus and calcium, but also magnesium and potassium. So the stoichiometry of the crystals was not typical because, of course, there are so many nutrients in urine competing for precipitation. So it was quite interesting reactions taking place. even more so when you add the biochar and add even more ions into the mix. I tried to cover a bit of everything quite fast. If you were interested, we have published this research and other research on source separation and pyrolysis. And thank you very much. I will be happy to take any questions either now or you can contact me via email.
Wonderful. Thank you so much. That's very interesting about the precipitation on the surface of the biochar. Definitely want to learn more about that. I believe we have 5 minutes still. You kept it to 10 minutes. Thank you. So we have 5 minutes for any questions. And we have one question already in here. It says, thanks for the presentation. Could you please share how was the cation exchange mechanism confirmed?
We essentially monitored the concentrations of the different nutrients, both in the liquid solution and on the biochar via ICP analysis. So we essentially saw what was there before and what after, and it matched exactly the amount that was given was taken and vice versa.
Thank you. I have a question for you. I'll jump in as other people type. You showed that there was a significant drop in the potassium levels in the urine over the 6-month storage period. And what do you attribute that to?
Do you mean during the precipitation during storage that
During
those
storage,
results?
yes. Yeah, I think you have.
It's likely some of the precipitates would have some potassium inside. So anything that, for these elements, anything that was eliminated from the liquid phase, we assume it's precipitation. So I assume some of it would be the struvite potassium analog that we found a lot of both after the biochar and before adding it during storage. So I think the biochar addition doesn't necessarily change the type of precipitates. It just is the medium that then makes their separation much easier and you can get a combined product. But it was the magnesium addition, the external magnesium addition, that then allowed us to get more precipitates out of the urine.
Great, thank you. All right, well, let's leave that here, and if people have more questions, just enter them into the chat. Thank you very much. So we'll go to our next presentation now from Rebecca Nelson. The topic is alkaline dehydration as a path for large-scale production of urine-derived fertilizers. That's with a question mark at the end. The question is this feasible? Rebecca Nelson is a professor at Cornell University in the School of Integrative Plant Science and the School of the Environment and Sustainable Development. Her research group works on circular bionutrient economy in collaboration with other researchers at Cornell and in the Rich Earth Network, and in the East African Circular Bionutrient Economy Network. Her work focuses on decentralized nutrient recovery from human urine in low-resource contexts and on the use of urine and other organic underutilized resources in urban gardening. Okay, Rebecca.
Thank you, Abe. Am I coming across okay? Slides?
Yeah, it looks great.
Great, thank you so much. So I thank you, Abe and Rich Earth Institute, and I've just modified my title here to be more to the point, redirecting nutrients from the lake to the land and examining the potential for alkaline dehydration for fertilizer production in Kisumu, Kenya. So our location there is on the edge of Lake Victoria on the Windham or Nyanza Gulf. So I think what's notable about our case here, if anything, is the partnership, and I think that is notable. We've got a great group of people in Kisumu, Charles Midega, Roy Odawa, and Florence Mwikali in particular from community-based organizations and the toilet company, group in my lab, some operations researchers and modelers, the wider Circular Bionutrient Economy Network, and we're building on the work coming out of Sweden on alkaline dehydration. So thanks, everybody. So I'll first start out with a bit more about the context, a little bit of a technical update, more about the partnership, and then sort of pitching a scenario for input from the Rich Earth Network that's here. Thank you so much for being here. So here we are on the edge of Lake Victoria, and you can see that the Nyanza or Windham Gulf is way more opaque than the larger lake, just signifying that when you've got a city on a pinched off body of water, you're getting a preview of what, what's going on with the water quality there. There's iterative gigantic fish kills. The fishery, including aquaculture, is a big industry there. The fish are dying off regularly as the lake suffers these harmful algal blooms. And so the idea is now here, where the urine from the city is going into the lake and killing the fishery, while agriculture is suffering from a lack of nutrients and water. And can we reverse that, just redirect the nutrients into agriculture, sparing both agriculture and the lake? So I'm going to start with the technical piece, recognizing that to pull anything off, you've got a lot of sociocultural work to do, technical, operational, legal, regulatory, but let's start with, my not particularly amazing, but, technical update here. So we're looking to produce both, greening this informal settlement we're working in with just the liquid urine, and then producing, some sort of fertilizer product that could move longer distances to the grain belt of the country, for example. Recognizing that in our group and others, lots of high-tech work is going on here, I'm going to be focusing on low-tech approaches that are suitable for use in our informal settlement. So we start out making biochar and a Kontiki, dumping urine on it, and then my partner Charles et al. Were able to show over these 3 years that water quench char looks like the nothing control, the water control, and the urine quench char could be, in the same statistical group as the chemical fertilizer treatment if you put similar amounts of nitrogen on there. It's okay as a fertilizer if you just peak quench. But I did a bunch of experiments both with wood and with maize stover. This is just the solid bars are quenching in air, urine, and water. So the stippled ones are when I then took the quench chars and soaked them in the ground and soaked them in a relatively large volume urine. I'm only getting up to, barely hitting 2% nitrogen on those chars. And the bioassays looked similarly as if I were not doing a whole lot for the plants with this material. So 2% wasn't really working for me. So this guy, Jean-Marie Nizigimana from Burundi, comes into my office and he's like, I want to make a dry powdered urine-based fertilizer. And I'm going, Jean-Marie, you and everybody else. So, but I started doing these rinky-dink experiments on alkaline dehydration. And so I was like, okay, let's do more of that, Jean-Marie. So we've made some just powdered ash plus lime plus urine. And to my delight, we were hitting 17% nitrogen on that product. And this is kind of a not very particularly great figure, but just the first time I saw that this stuff was great fertilizer. If we put a lot on, we kill the plants, cut that in half, and we get a jungle, cut that in a third. We're still performing well above the full synthetic nitrogen fertilizer rate, and that's the zero fertilizer, and that's the half. So this stuff seems to be, fine as a fertilizer or bioassays. So we bioassayed on soil. This is an eggplant harvest. Again, we're benchmarking well against the full synthetic dose in the greenhouse experiment. So we started, again, following the Simha et al. Literature. We started drying biochar with and without ash, and urine with and without ash and biochar, both in Ithaca and in Kisumu. This is a Kisumu bioassay showing that we're calling Golden Grow product benchmarks well against synthetic fertilizer in their tests. So I just want to show you one experiment of the series that we've been doing. In this case here I am, my grandmother used to harp on, waste not, want not, and similar. Here I am harping to my grandson about how he needs to be working on, urine-derived fertilizers in the future. He's bearing with me there. But so this particular experiment in these deli cups was 200 mils of biochar per cup. And there's one set that's 6 reps each of pine wood char and maize stover char. And then we put, the question here is like, how can different ratios of urine to biochar, how do they perform in terms of getting rid of water and keeping nitrogen? So, and also there's a water treatment. So we could, see an increasing, so this is like refilling for a couple of weeks to the reference weight of that unit to keep those different ratios of urine to char. So as we increase the ratio of urine to char to, more than the char, and then variously less than the char, on par with the char. We're losing more water if we add more P, but with diminishing returns. But we're not getting much more nitrogen beyond the first couple, beyond 100 mils. A half volume of urine wasn't any better than 2.5 volumes of urine. So what's going on here? We're measuring the ammonia losses. They're all over the place. Sometimes we have none. So what I kind of conclude is, so sort of dividing the total nitrogen by the urine volume, you can see that we're getting less and less efficient in terms of ammonia capture, nitrogen capture, sorry, as we increase the volume past that very first lowest level of urine volume. So maybe it's this calcium carbonate crust that forms as we increase the amount of urine. And I think also we're not, because of this formation of the calcium carbonates, I think the pH is slumping down, and we need to jack up the lime quantity to keep our urea. So I think it's a question of managing the pH and maybe managing this crust problem going forward. So now just sort of, that's kind of where things stand in terms of our, wringing our hands on the technical level. Just to get onto the operational level, we're part in the East Africa context of the Circular Bionutrient Economy Network. And Johannes Lehmann, my colleague here at Cornell, had a lot to do with bringing this big group of fabulous African talent together that work on, commercializing biochar, carbon credits, excreta, recycling. And that through that network, we've gotten to know the people at Synergy quite well. They have the Fresh Life and Regen Organics sub enterprises. So they're based in Nairobi. They're the biggest in the world, most innovative in the world, as far as I know. And they've come out to Kisumu with a secondary site where they're making toilets, but they don't have the Regen Organics fertilizer manufacturing capability coming with the toilets. So our second big partner is called the Kisumu Young Agripreneurs, or KIA, led by Roy Odawa here. So they do a lot of networking within urban to rural populations, sending out seedlings, bringing back, aggregating product. So I was kind of trying to prompt them to make a team up between Fresh Life and KIA, with the idea that if we representing our gang with the young agripreneurs, if we could collect the excreta and make fertilizer, urine-derived fertilizer, biochar, alkaline dehydration, pea-powered composting, like soldier flies, less nutrients would go to the lake. We could support agriculture. The fact that we're doing the servicing could mean we reduce cost to Fresh Life and to the users. That would enable the expansion of the container-based sanitation operation, a denser toilet network, which would benefit us as we collected the excreta. We would be improving sanitation and making more money. In my simulation modeling, I'm picking up a positive feedback loop here. So that brought us to the table in our Airbnb there. And that's the woman who runs, Florence Mwikali, who runs the Fresh Life operation at Synergy, my research partner, Charles Midega, Roy Odawa, head of KIA, Eric Abala, who's running the CBEN operation, or one of the leaders of CBEN. So we've signed agreements amongst us. And so here's a map of the neighborhood. So you can see a relatively prosperous neighborhood has one look from the sky on a map, and the informal settlement has quite a different look. So this is where you can profitably collect excreta. They're not sewered. The proceeds are going out to the lake. The potty network map looks like this, and we agreed to initially start with this first 80 toilets that are near the KIA location there. So we want, again, we're collecting the liquid, moving it around. We've got this nice little tricycle, I call it. We've got a biochar capability here. We're getting going. So the plan I want to put out there is that we collect the urine with lime, calcium hydroxide, maybe dry the sludge at the bottom as a calcium phosphate, redose the liquid, make the solid chamber material into biochar, trying to figure out whether we're better off drying in a trench or drying on racks in the high tunnel, and then either collecting water if the price of water is high at that moment, but in any case, making this fertilizer product that's got nutrients, carbon, and liming potential, the soils being dominantly acid in that area.
You're at the 10-minute mark, Rebecca.
Oh, okay, gotcha. Okay, anyway, just to wrap up, we're doing system dynamic model to try to figure out how to make the business aspect work. I'll go light on that given the time, but appreciate the trying to figure out how the business model will work, and just saying we're linked with multiple big farmer networks from rural to urban, and these people shown here are all super into urine as a fertilizer. So we're optimistic that we can. I think we don't face impossible obstacles to redirect the nutrients from the lake to the land. And I thank you very much, and it would be very grateful for any technical tips on whether this scheme that I'm presenting makes sense, or if you have any friendly amendments or suggestions. Thanks so much.
Thank you so much, Rebecca, for your presentation. That was great. And I'm glad you shared that slide again with the urine going to the left or the right. That's a very powerful image. I've not seen that one in your presentations before, but I'd like to steal it.
Oh, please, yeah.
You ended that with a question for other folks with feedback or questions or input. I'm
Yeah, we have
not.
some real superior engineers here on the, I hope amongst the 50. I hope somebody can help me, guide me here.
Well, I can talk faster than people can type. So we don't have questions in, but I'm sure people are typing. I will ask while that's happening. You're doing this alkaline dehydration and air drying. I know that carbon dioxide coming in and becoming carbonate can be an issue. What are the prospects for using acid instead? Is that potentially viable, or are there obstacles to using acid to avoid that problem?
I love the beautiful amber liquid you get with acid, but the soils are very acid. So the fact that my product is full of lime is an actual benefit. So I was thinking of doing some acid dehydration, just so we could make a bespoke fertilizer product that hit the pH requirements of whatever zone we're working for at that moment. Like we would work with the farmers to do pH testing, but so far our partner farmer research networks have found that lime really, really helps yield in this region. So just the fact that lime is grody and hard to work with and everything, but for me, it becomes possibly one of the more valuable constituents of our product. So that's why I'm sort of going for the high pH. Yeah, so I don't know. I mean, I think everybody who's in this aspect of it with me is suffering too by the very difficult chore of trying to get rid of water. So and we'll be dealing with multiple IBCs per week, even at this first deal of 80 toilets. We'll be dealing with tons of urine per week, just to start out. So I really need to get rid of water. Recovery costs, jeepers. Yeah, no, I'm not there yet. So yeah, as I started to say, I'll be on sabbatic early in the spring, spending some months there trying to figure out. Yeah, we're really trying to figure out how to make money. And I don't, I know the price of a small bag of lime, but can we start getting tons of lime at a way better price? There's just a lot of pricing issues. That group of people in the community-based organization, they have worked for Fresh Life, so they know about it. I don't think there's a lot of the human obstacles or the regulatory obstacles, because all the deals are signed, including with the authorities, to make it happen. But whether we can make it happen financially, I don't know yet. I mean, what is the real price of biochar that we'll face, either making it or buying it? Hopefully, that with all of this energy in Kenya around carbon markets for biochar, a lot of companies that I on the WhatsApp every day, zillions of messages from the biochar company people. I just don't know what the pricing is going to really be.
Okay, great. Thank you. I think we should move on at this point. There is one more question though that I'll call your attention to from Jenna Senecal, that they worked a lot with ash in Sweden, but stepped away because people worried about heavy metals. So if you have any info on that and your stakeholders, if they're concerned, you could please pop that into the chat. And there may be more questions, of course, coming in. Our next presentation is from Joseph Lybik, also at the University of Michigan, same as our first presenter. The presentation is Enhanced Ammonium Bicarbonate Precipitation via CO2 Sequestration with Hydrolyzed Urine. Joe is a PhD candidate he's a PhD candidate in environmental engineering at the University of Michigan, where he's advised by Professor Nancy Love. His research is broadly focused on optimizing nutrient recovery from wastewater systems, with an emphasis on leveraging data-driven models and source-separated waste streams. He works closely on maintaining the University of Michigan's building scale urine diversion and nutrient recovery system, where he investigates real-world deployment of source separation technologies and the production of a variety of different aqueous and solid-state fertilizer products. So Joe, if you're there you are. Go ahead.
Awesome.
I see your screen.
Yes. Let me see if I present it.
Looks good.
All right. Awesome. Thank you so much, Abe, for the introduction, and thanks to everybody for coming out to the conference. It's such a privilege to be able to talk to you all today. Like Abe mentioned, I'm Joseph Lybik. I'm a PhD candidate at the University of Michigan and going to be talking a little bit on some preliminary findings we've had in trying to produce an ammonium bicarbonate fertilizer product from hydrolyzed urine. So we all know, by now the many benefits of p-cycling, of urine diversion, but there are definitely some co-benefits that may oftentimes go overlooked that I kind of like to bring up in these sorts of mediums. One is how urine diversion can actually help increase the treatment capacity of downstream wastewater treatment plants and allow us to do more with our existing space and wastewater infrastructure, so kind of an intensification benefit. Another is how p-cycling can reduce fresh water usage and how that plays out for us at the University of Michigan. We're starting to get approached, our group is starting to get approached by a lot of facilities and construction teams at the university that are working on new dorms and buildings who see p-cycling as a way for them to reduce the size of their sewerage connections, which is a really big capital cost. If you have less flow going into the sewer, you can reduce the size of those connections and decrease your construction costs. And then, lastly, as sort of a tease for this presentation, we're sort of in this era of net zero. And it turns out that urine is a pretty good CO2 absorbent. And so it can possibly be used as a tool to also help us limit our greenhouse gas emissions. So those are some of the co-benefits and the things that our group at Michigan thinks about when we're engaging in this research. But obviously, one of our primary focuses is to demonstrate nutrient recovery and the production of safe fertilizer products. And we do that in our on-campus facility that we call the Nutrient Recovery Facility. You may have seen from the video tour yesterday, we have this urine collection and processing system. It involves collecting urine from a couple urine diverting fixtures in an on-campus building. We then pasteurize that urine and then cryoconcentrate it to produce a concentrated liquid urine-derived fertilizer. You'll see a lot of this equipment has Brightwater Tools branding on it. They're partners of ours. I do have to disclose that the University of Michigan has some financial ties to them. But from that concentrated urine-derived aqueous fertilizer product, that is a permitted product in the state of Michigan, so we actually can apply that.
Joe, I'm not able to hear you anymore. Are other folks able to hear you?
I hear him fine.
Oh, I think that it's audio settings just automatically changed in my computer. I will be quiet and let you go ahead.
No worries. Thanks for letting me know. If anybody else has issues, feel free to butt in. Our fertilizer product is licensed by the state of Michigan, so we're actually able to apply that product outside of campus and do field trials and research on that, which is really nice. We're also able to take that aqueous fertilizer product and put it in a struvite precipitation reactor. So we can also obtain a solid state struvite product that Jordan showed earlier in her presentation. So we end up with a solid state struvite product and then a nitrogen-rich aqueous fertilizer product. So here's a picture of that struvite product, and you saw some of it in Jordan's presentation as well. And we're really starting to go all in on producing solid state urine-derived fertilizers, as some of the previous presentations talked about. There are a lot of advantages to solid state urine-derived fertilizers due to their ease of storage and transportation, their ease of use with existing fertilizer equipment. So especially at the University of Michigan, our grounds crews tend to prefer solid state fertilizers. But they also can be made slow or controlled release, like Jordan had mentioned, allowing for potentially less runoff and decreased applications on fields. And they may be a little bit more palatable in terms of their odor and use for non-farm applications. While the production of struvite, a solid state phosphorus product has been really well documented and researched, there's much more nitrogen in our urine than phosphorus. So really a motivating question for us and for this work is, can we produce a solid state nitrogen-based urine-derived fertilizer? So it turns out that we can look to the industrially scaled carbon capture technique called the chilled ammonia process to help us investigate this. Ammonia is a really good CO2 absorbent, but to use it in practice, the systems need to be at really cold temperatures to decrease the volatility of ammonia and decrease the losses that may result from it being lost as a gas. A consequence of those decreased and low temperatures is that the solubility of ammonium bicarbonate also decreases. And when you saturate ammonia with CO2 and you decrease the temperature, you hit that precipitation, that saturation precipitation limit of ammonium bicarbonate, and you get a solid. For these systems, this can be a nuisance because it can clog up the equipment and you lose some of your ammonia. But for us, that's something that we could maybe potentially leverage and recover as a fertilizer product. Also, it just so happens that we have access to really high-strength ammonia-based absorbents from our cryoconcentrated urine fertilizer. And also, we're working at these low temperatures and even lower temperatures down to -5, -10 degrees C from our freeze and cryoconcentration process. So we thought, why can't we see if we could recreate, this cold chilled ammonia process in the lab with urine and obtain a solid ammonium bicarbonate product? So that's exactly what we did. We started with just some proof of concept experiments using a semi-batch bubbling reactor, where we essentially just took some synthetic high-strength ammonia solutions and bubbled in a CO2 gas mixture at very cold temperatures. This is what it looked like in the lab. They were pretty simple experiments, basically just bubbling in a bunch of CO2 into some ammonia solutions. And we were actually able to obtain some solid precipitation in the system. We ran a couple solutions and obtained solids from a high-strength 5-molar pure ammonium chloride solution, and then what we called a high ionic strength solution, which included 5-molar ammonium and then other ions that are present in urine, such as sodium, potassium, phosphate, magnesium, calcium, things like that. In this pure ammonium solution, we saw 19% of our initial nitrogen was lost in solution, and we were able to recover 10.5% of that. And then in the high ionic strength solution, we saw a 22.5% loss of initial N, and then a 13.7% recovery. Now, some of that discrepancy between the lost and the recovered is due to some losses of the solids during the filtering and the drying steps of our process, but there was also definitely some ammonia volatility loss, so some loss of N as a gas. Now, how do we know that what we recovered is ammonium bicarbonate? We ran our solids through X-ray diffraction and then compared them to a reference ammonium bicarbonate solid that we purchased off the shelf. And you can kind of see how the peaks of these of our samples on top and then our reference solid on the bottom all line up, confirming to us that we did indeed create an ammonium bicarbonate product. So another big takeaway from these initial experiments was the impact that pH had on our system. The pH drops over time. So I'm showing you just pH versus time on this plot as CO2 is absorbed into the system. And then it starts to level out a little bit as saturation of the system occurs. So at this high pH range, we have higher ammonia availability and therefore a higher rate of CO2 absorption and a higher capacity for CO2 absorption. And then at this lower pH range, we start to see saturation of the system with CO2, and that's where we get precipitation because the equilibrium is now shifting towards ammonium and bicarbonate ions. Okay, so we proved that we could produce solids and some synthetic analogs of concentrated urine, but our recoveries were pretty low. And one of the reasons for that was we weren't getting enough carbon into our system. So we've been working on upgrading our system to a column reactor, which I'm showing here. Essentially, we're just putting CO2 in a CO2 gas mixture in the bottom of this column, and then we're circulating our solutions in from the top and out the bottom. This is what it looks like in person, and then we're monitoring a bunch of operational parameters via some sensors, things like pH and conductivity and temperature. We also added a pH controller to try and see if we could maintain the pH at a high pH range so that we could increase the absorption capacity of the system. So we have run some initial experiments. We have a lot more to do in the column reactor, but what we are seeing is fairly promising. What I'm showing here is a comparison of the carbon concentrations. So this is a normalized carbon concentration on the y-axis versus time on the x-axis. The results on the left are from the column reactor, and then on the right are from our batch reactor. And what we're seeing is that our column reactor is able to absorb carbon at a faster rate. So you can see the slope is a little bit higher. And actually, what we're also seeing is that we're able to get more carbon into the system by using this column reactor. And why that's important to us is if we model out using some equilibrium speciation modeling, the percent recovery of nitrogen that we can increase our recovery of nitrogen if we increase the ratio of carbon to nitrogen we have in our system. So by using this new column reactor, we're able to increase the ratio of carbon to nitrogen in our system and potentially increase the amount of nitrogen that we can recover. Other parameters that influence the CO2 absorption and recovery that we see in our system are certainly temperature. So I'm showing 3 different temperature ranges here. And as you get colder, your percent of nitrogen that you can recover increases as well. I talked about pH, but also things like the liquid and gas flow rate, your initial ammonia concentrations. And then it turns out delivering CO2 via bubbling is pretty inefficient, so you can do other methods as well. We're exploring across all these parameters. One that's particularly challenging is controlling the pH. Urine is very buffered. And so to try and limit the amount of external chemicals we're adding to the system, we've been working with Will Tarpe's group out of Stanford to investigate the use of electrochemical pH control for in situ pH adjustments. The results I'm showing on the right are pH versus time. Basically, what we see is that we can't counteract the pH change from the CO2 absorption, but we can kind of slow it down so we can hopefully increase that carbon absorbing capacity of the urine by keeping the pH a little bit higher for a little bit longer.
You're at 12 minutes, Joe. Sorry.
Okay, thank you. No, you're fine. There's a long way to go. This last slide. We need to prove that we can do this in real hydrolyzed urine, but definitely there is potential. We're also exploring using a new reactor with a hollow fiber membrane to increase absorption rates and capacity, and going to do some additional equilibrium modeling to assess the viability and scalability of the system. Big thank yous to a bunch of different people, and thank you so much for the time. Appreciate it, everybody.
Great, thank you, Joe, for that very technical and detail-packed presentation. I followed it because we've been over it many times, but that was the first time I've seen the actual product in a dish, so that was great to see that made real. If folks have any questions for Joe, please pop those into the comments. Questions, clarifications, suggestions. One of the things I think is so interesting about this, and disclosure, we've been working together and putting in proposals. So I have a prejudice for this project, but yeah, so interesting to see this clever leveraging of solubilities and the pre-existing conditions in urine. Well, maybe I shouldn't have cut you off. But I bet people are typing. It takes a moment or two. Any other closing thoughts or related thoughts you want to share while we wait for the questions to come in?
Yeah, I mean, just that I think we need to show that this can work in urine. One of the things that I've seen that's potentially helpful is that urine has a lot of other ions that also can help absorb carbon. So it may be a little bit better than just a pure ammonia solution, which is something that I really want to investigate further. And yeah, just a lot of potential for the system. We know we probably won't be able to get to like super 100% recoveries, but hopefully a decent amount of recovery that we can get from the initial ammonia concentrations.
Great, thank you. Well, I think we'll just we're actually at the 15-minute mark. So there is a question about why the move toward hollow fiber reactors or the CO2 diffuser. Another one about the vision for how it will be scaled. So if you can address those and others in the chat, that would be great.
Absolutely.
Thank you. Okay, now we will move to a presentation from Rachel Binstock of Wasted. The presentation is bringing urine-derived products to market. And as a bio, after 10 years of regenerative farming, farm education, and off-grid living, Rachel went back to graduate school with the aim of scaling climate solutions. She now serves as the chief of staff at Wasted, working on their labs team, operationalizing nutrient recovery. She leads the regulatory work, go-to-market strategy, and oversees fertilizer operations. Hi, Rachel. Are you able to share your screen?
Hi, everyone. Yes.
Yes, you are. Good. We see that. Thank you. Go ahead when you're ready.
Hang on. This is not allowing me to see my notes. See if I can do it in a different way. There we go. Can you guys see that?
We see it, but we see it as like as a subset of your screen. We see the whole tab you're in.
I see.
Okay.
Let's exit that. And give me 1 second. I'll pull these up. Sorry, everyone. 1 second. Okay. All right, great. Hi, everyone. Really great to be here today. It's funny to be coming at the tail end of a lot of technical presentations. This is going to be a bit more of a summary of our market research and where we're at with bringing our fertilizers to market. But I think that's important. It's both sides of the coin here, as we are all a part of this ecosystem developing technologies to recover urine and then to place them in the market in ways that make sense. So as Abe shared, I lead our closing of the loop work here at Wasted. That means everything related to fertilizer, including overseeing our engineering team, working with regulators to set up legal pathways and unlock our work state by state, and also the go-to-market strategy work, which means I've been doing a lot of market research. I'm incredibly grateful for this community that's committed to urine recovery. We're here today because of you all, and I'm really excited to start populating the conversation around market trends and needs so that we can properly scale technology and also fund it. And all comes down to, as far as we understand it, to financial incentives and levers, unless you have grants to offset these costs. And so identifying those are key. At Wasted, our financial incentives are as follows. We have savings from tipping fees as waste haulers. And so that cost, instead of outsourcing it to wastewater treatment plants, we get to keep it and use it to recover nutrients at our hub, and via revenue opportunities from obviously the sale of soil amendments. That could also look like green chemicals or other things that you want to do with that waste. And today I want to give you a little tour of our product and of the market research. So many of you might have met WeBloom. This is the first product we've brought to market. It's our flagship product. We soft launched it in December of 2024. We sell it direct to consumer via our online stores, and that's at notwasted.earth. WeBloom is the first urine-derived fertilizer licensed in Massachusetts and California. It's also licensed for sale in Vermont, Rhode Island, and we just got a green light from Maine, as well as Washington State, so those are in process. That's a big deal. Maine's been very concerned about PFAS and land application of biosolids. This product has an NPK ratio of 5:26:0. It's not water soluble, and so really for this crowd, it's struvite. That's what we're making, as many of you are making in your labs as well. The way we talk about WeBloom is it's good for roots, shoots, buds, and blooms. It's good for anything that phosphorus is good for. Root establishment, nutrient uptake, boosting plant, boosting blooms. We call this product a superfood for your plants, and we sell it as a specialty fertilizer in the home and garden market here in the US. As you all know, the way we make struvite is we pasteurize it. We currently use a Brightwater Tools pasteurizer, and then we precipitate it out with a rich earth-filled reactor. And we do this because we also make a second product called Golden Grow, and the soils here in Vermont are quite high in phosphorus, so we pull phosphorus out, we bring the liquid product to farms, and this then we sell to backyard garden at hobbyists. This product wholesales for $10, and MSRP is $20, so the value that the end buyer will purchase it at is $20. And we have sold about 300 units of WeBloom to date. It's really our flagship product, and it's also our Trojan horse. It's entering into the market as a product that doesn't look or smell like urine, and that's important, which you'll hear about next. So here's a little bit of a breakdown of what we're learning. To create these successful products, to bring them to market, we're learning that we really need to know what the consumer wants and needs, and it really depends what our distribution pathways are. So here's a little snapshot of insights. And I'd love to hear more from others about what they're learning. I got a little bit from Joseph about the smell. I've heard from a couple others in this industry, sort of like what they're learning, but I think it's going to be helpful for us to start cultivating the crosstalk here. So what we're hearing from customers and users are the following. Is it effective? They want to know the value proposition upfront. They want us to communicate to them why they should be buying this, what the product promises, and how it's going to help their plants. So really giving that descriptive language and that application method. They want to know if it's safe. This is generally an assumption that fertilizers, often chemically based, could be unsafe to handle, unsafe for their pets, unsafe to have around their house for their kids. And so this creates a conversion challenge. And so safety claims, we are understanding are very, very important to communicate as they bolster trust in the product. They want to know, does it smell? Most consumers, this might be a little bit different for farmers, but most consumers are not really interested in handling a product that's stinky. And when they hear it's made from pee, they ask, does it smell, implying that they wouldn't purchase it if it does. And so making sure we manage for odor is essential in producing products that will be absorbed into the market. How was it made is a question that we got over and over again. And so communicating what process the waste underwent helps bring the consumer along with us and grows confidence and boosts trust in that product, that it's not just greenwashing. And then they want to know usage. They want to be told exactly how to use this product and communicate the sort of like directions very clearly. When we work with farmers, it's a bit different. We're working with a different product, which is Golden Grow, as I shared with you all. And Rebecca, I love that we've arrived at the same name for our products. It's very sweet. Yeah, Golden Grow is essentially our effluent product for making our struvite, for making our wheat bloom. So it's pasteurized and phosphorus stripped. And that is licensed to sell in Vermont and Massachusetts. Or I should say, rather, it's legal to use in Vermont and it's registered in Mass. There are different insights when it comes to farmers. They, first and foremost, really want to know that it's safe. They know where fertilizer comes from, fish guts, blood meal, bone meal, lots of other sorts of like industrialized waste from the ag system. So human pee is not out of sort of the realm of possibility for them, but they do have concerns around emerging contaminants. So when we speak to farmers, it's super important to talk about fecal coliform, salmonella, heavy metals, PFAS, pharmaceuticals, all of which we have amazing answers to thanks to this community. Farmers are often really looking for fast-acting nitrogen. They are often applying throughout the season, and they're a more educated end user when it comes to soil science. And so they know that nitrogen is nitrogen, but many of the growers want to be thoughtful about what amendments they're using, and they know that there are long-term impacts to using other kinds of products. So it's a nice alternative to non-synthetic for them. They're often looking for biologically derived. A non-stabilized product is tricky, but is possible to move into the market, we're finding, but it's best suited for fertigation, where there's not a lot of handling of the product. So fertigation meaning being pulsed through water systems, drip irrigation, things like that. We've also found that most farmers would use this if it was cost competitive, but unfortunately, I'm sure this has been the case for a lot of others who've been building financial forecasts around the fertilizer sort of like reality, is that it's going to take serious economies of scale, so hundreds of thousands of gallons per year, just with pasteurization to make a product profitable. And that leaves out all the kinds of go-to-market costs, all the transportation costs if we're moving this around. It doesn't start to consider stabilization and concentration, which are, as we heard, going to be key. And this means that competing with commercial ag is going to be virtually prohibitive for many of us, unless we operate at very, very, very large scales, or unless we're able to command higher price points for our products. So for all of these reasons, at Wasted, we're moving forward with a focus on retail so we can demand a higher price point. and get us to profitability. And we'll continue to be working with farm partners with Golden Grow as a secondary product. Retailers are another category. They're often open to trying it, but they generally see that specialty fertilizers are really hard to sell. So when we're looking at WeBloom, it's a harder sell than something more balanced NPK wise. They've also shared that they're concerned about the public perception, and they really want to know that other people have adopted it. So they're all asking, well, who else are you working with, and have other garden centers picked this up yet? They want to know that it's been trialed and tested, that it's effective, and they want it to be properly priced in line with other fertilizers. So all of these concerns are helping us learn that we need to manage to these concerns as we bring this product to market. And then a few other challenges for retail. There's lots of other products out there, so there's lots of noise on the market. To compete with, we have to register our products state by state in the US to maintain licenses that allow us to sell. And so that creates another cost element. And we also pay tonnage fees for, we report on sales at the end of the year and pay per ton. And then for us in our operations as a vertically integrated company, there's a sort of equilibrium that we're maintaining between collections and sales. And that will be the key for us in terms of scalability. So yeah, the last one here is that many customers are used to fertilizing with granules. This came up in Joseph's talk as well. And so being able to granulize products might mean that there's more market absorption because that's what they're used to using, both on the farm side and on the sort of like backyard garden scale. So
You're at the 12-minute mark, Rachel.
thank you. Okay. Let me just run through this quickly, which is that organic unlocks a higher price point. You can see ag and retail here, and that's why we've been moving to look for pathways to get organic certification. We've been working with a consulting firm to help us navigate the National Organic Standards Board. And the thing I really want this group to know is that this process may be helped by a demonstration of interest, that farmers want to see the National Organic Standards Boards take up a petition to consider urine-derived fertilizers for market. And so if that's something that you are interested in working with us here in the US, please reach out. We'd love to partner with you on this. It's probably going to look like asking for a variance. I want to share a little bit about our regulation reality. We have been working on regulating the regulatory pathway in Massachusetts, and we're starting to do this elsewhere as well. And what's working, we're seeing in our strategy is that we license a fertilizer first. So there is a end use for the product, and then we go to the environmental protection entity and say, hey, there's an end use for this product. Can you license us for processing? We're currently in that process with Mass DEP. They've given us a couple pathways. But as we look into other states, just so you all know, there's a few other alternatives that we're looking at, including demonstration facilities and co-location with site assignment. So facilities that already have waste treatment assignment. I also know that moving forward, we're going to be wanting to push for a distinct treatment pathway, so source separated urine distinct from public health criteria of biosolids, and that looks like a urine to fertilizer production facility understood as separate from waste processing, and we'll continue to use that language where we can and where it makes sense. Just a quick report out to this community about where we're at with emerging contaminants. WeBloom measures at least one order of magnitude below national limits for biosolids. We routinely measure and non-detect for fecal coliform in our pasteurized and liquid urine products. Pasteurized liquid products, and routinely measure non-detect for salmonella in our WeBloom. And we test for 40 PFAS compounds according to the EPA 1633 method, and measure non-detect for 40 out of 40 in WeBloom, which is really important for us to report out to all concerned folks. Yeah, and we're planning to bring a new product to market called Tinkle Tonic. This will be a liquid product with a more balanced NPK ratio, and we're looking forward to sharing more on that soon. I'll end there.
Wonderful. Thank you, Rachel, for that that multifaceted look at the opportunities and challenges of bringing urine-based fertilizer to market.